Here's the VCA, one of them that I hastily put together based on a 13700, and I'm just using this little audio generator because if I had to put this guy on the same desk with all of this, there'd be no room. Alright, so what we can hear here is that's the VCA modulating the output with the triangle or the sawtooth wave on the from the EG. Let's I'll switch to let's see if I got it here. All right, now we're going to see. There we got a triangle. Hey, so the boards came back for the VCA, for the voltage controlled amplifier. Now I've got two separate boards here and we can do a little comparison. This is from Advanced Circuits. This is called their bare bones fast service. So you'll notice there's no solder mask, meaning this board doesn't have any green or blue or purple stuff on it. It's just the wires on the substrate with holes, with plated through holes. So these wires, if you were to touch them, you'd be shorting things out. Not like a regular circuit board, like one of these circuit boards. You'll see the wires are all coated underneath this green stuff. That's called a solder mask. Okay? And so if I was to touch a wire onto here, nothing would happen. However, on this bare bones board, if I was to touch wire or anything onto here while the parts were on it, it would short it out. Now, the purpose of these bare bones boards, according to Advanced Circuits, is to get a prototype going quickly, and then once you get your prototype going, and this is about the cheapest way you can do it. This is a their El Cheapo service, and it's pretty quick. I got these boards back in a week from the time I sent the design in. So that's pretty good, except they were expensive. I paid 100 US simoleons for 5 of these. So not entirely super dirt cheap. And if I want to have these made officially in the same way these are made, and these are Advanced Circuits boards as well, they'd cost me around $20 to $30 a board, even though they're really tiny. Now, I'll say this about Advanced Circuits. Their products are pretty superior, and I got to say, their boards are, this is a very well-made piece of stuff. Now, the other boards that I got in, I got these from OSH Park, which is recommended as well on the Adafruit website. And these have a solder mask, and they even have my stencil, my my drawings. So it's got all the, you can see where the resistors go on here. I had to take a Sharpie and write everything down, which is even top or bottom on here. I've got my silk screen, top and bottom silk screen. See, all I have on the bottom is V1.0. I got the solder mask. I've got all the wires on there. These boards cost me $28 for 3, and I got them in about a week and a half. Now, I don't know if that's typical, but $28 for 3 seems to be about $7 a board versus about even $20 a board for these, and a lot more once I go production. So for a hobbyist, this is probably not such a bad idea, right? And I've got one other board I will show you. I had some of these VCO boards made by Seed Studio, and you'll recognize these if you watch the last video because these are the same as these. Now, these came in from Advanced Circuits, the green ones, and these came in from Seed Studios. These cost me about 30 bucks for 10. Now, they're made in China and they were shipped over, and they took 2 weeks to get. All right, but in terms of quality, I'd say, it's clearly made of a different material. It doesn't look like it's as tough a material. This looks more like a, like a fiberglassy G10 kind of thing, and this looks kind of more like it's got some, I don't know, paper or silk or whatever. But, as a maker, this is perfectly fine, and it's one tenth the price. Now, if I was going production and if I was going to go and build these things commercially, I would probably stick with advanced circuits just because I know I could do a deal with them on volume, and I know their product is ACES, is A1. But for a hobbyist, OHS Park, purple, pretty cool. The only negative about OHS Park is you get these little dingers, because you know what they do is the boards come and they I guess what they do is they're kind of together like this when you get them, and you got to crack them apart. So what, right? I'm a maker. I'm not a production guy. Okay, so the VCAs are in. VCAs are in, and I have put one together, and that's not what this video is going to be about, because the VCA, the voltage control amplifier, is working just fine, and it's kind of boring just to watch a signal go up and down. What I wanted to do on this video is do the EG, and my idea for an EG is that I was going to use the Arduino and generate a signal from the Arduino that will then modulate the voltage control amplifier. Okay, now here's the thing. There's a whole bunch of things here. All right, thing one. Thing one is this VCA board's running at 15 volts, and you'll notice I've got the MTA 156 here, and it's going to be plus and minus 15 volts. Standard analog-y MOTM kind of, Eurorack-y kind of voltages. These Arduinos certainly don't run at that. They're running at 5 volts, right? 0 to 5 volts, single-ended. And in addition to that, your typical Arduino is not going to create for you a nice analog-y signal. It's going to create a pulse width with modulated signal that you have to convert back into analog. And that's, one of the problems with Arduinos in general. They don't give you an analog out. You got an analog in, but you don't get an analog out. Now, how can we get over that? Well, one thing we could do is not use an Arduino. I could use a Teensy video on it, and it's got awesome audio capability. It's got an awesome DAC. It converts digital to audio or analog really, really well, and it's got all kinds of processing software that goes along with it. I could use these, and I might yet resort to this. Given all the trouble I've gone through so far, though, I may not. The other thing I could do is go to an Arduino Due, which has got a digital analog. It's got 2 DACs in it. In fact, right here, see it says DAC 0 and DAC 1. I have officially blown up DAC 0, messing around with it. It no longer outputs a nice analog signal. I've noticed others on the Arduino blog site complain of the same thing. It's easy to blow out the DACs. But if I wanted to get a true analog signal from the computer, the Arduino computer, I could do it that way. And I might yet do that. But I figured, why give up? Seeing as how we're doing this for fun, I don't have a deadline. Why not just try to convert the PWM to an analog signal? Now, there's a couple ways to do that. There are many ways to do that. Now, the way I have eventually chosen is to use this chip. But the first thing I want to show you is, and again, I'm presuming all you guys and girls know what PWM is. And I'm not going to give a tutorial on PWM. You can go look that up. But what I'll do is, just for the sake of keeping us all on the same page, let me draw a little picture. So basically, seeing as how the Arduino can't output anything other than a 0 volt or a 5 volt signal, if you want to get an analog signal, what you do is you diddle the voltage output around between 0 and 5 volts, and you try to collect as much of the voltage. Let me say you're trying to collect as much of the current as you can. In fact, you're doing an integration. Integration is a calculus word. I know that. It just means add. You're just adding stuff up. So what I want to do is, if I've got, if I want to make an analog output, analog is kind of a wavy thing. It looks like this, right? But I've got the ability only to output voltages that are either, up here or down there. I can't do a little wavy thing. So what do I do? So if I want to make a nice sine wave, what I do is I do pulse width modulation. As time goes by, so time is going by, I output, in the beginning, I may just output a little tiny sliver of a 5-volt signal, and it may only be for some very small part of a second. And then as time goes by, I want to try to output a little bit more here. I want this voltage to be a little higher, so I might output a sliver that's a little thicker. And then when I get way up here, I want to represent a voltage that's bigger, so I'm gonna output a really thick one, and then a really thinner one, and then a really thinner one. And the thing is, if you add up all of the electricity, the current, whatever you want to call it, that's represented by these times. Now this is time going by here, so I got a little sliver. I just and a little chunk because see, I can only output +5. I can't output any voltages less than that. So the thing that I have to modulate is the time, so that the area of this square, the contents of the area of this square represents this value. Contents of the area of this square represents this value. Contents of the area of this square represents this value, and so on and so forth. And that's called pulse width modulation. So what I'm looking at is, instead of looking at a wave that is doing this, I'm looking at a wave that's doing this, and I'm adding up the amount of black stuff that I get and calling that one of these numbers along that wave. Okay, now, all right, I realize it's kind of a feeble explanation. What is the magic adder that adds up all that stuff? In the case of the circuit we're going to use for the synthesizer, the magic adder actually is going to be this guy right here, which is a linear technology 2645. But I'll get to that in a second. There's a really easy way to add up those squares, those voltages, and that is to use, let's see, we'll bring this over here, to use one of these little guys right here, a capacitor. Capacitor stores up voltage, and it stores up current actually. So it stores it up, and as the current starts filling in here, the voltage starts going up. And so what's happening is, as time is going by, I'm filling up this capacitor. I fill it up for just a short time, and the voltage on the capacitor goes up as I start filling it up. But once I stop filling it up, it goes down again. All right, so then I start filling it up again on this one, and the voltage goes up, and then I stop and it goes down again. And then when I get this big one here, I fill it up for a long time, and the voltage kind of maxes out. So what happens is the voltage on this capacitor sort of does this sort of thing as this pulse width modulated wave goes by. And if you kind of look at the outline of this, it looks like the outline that we want. So what you do is you put a capacitor here, and I'm going to put a capacitor here, and this is a 0.01 microfarad junk box capacitor that I had laying around. There's no magic to this. I literally just, grabbed it out of my junk box. And what we're going to do is a little demo on how to turn a pulse width modulated signal into an analog signal. Again, actually, you're going to make a little digital analog converter. All right, so how are we going to do that? Let's look up here, and I'm going to go to my Arduino code. Now, a couple of things I learned about the Arduino in the process here. But first, I want to show you what we did before I explain the pain and suffering I had to go through to create this. Okay, so I'm creating a variable here, a table full of values, and there are 3 waves that are going to be stored in this table, and each wave is going to have 120 points. And so the first wave, as you can see, as soon as you see this thing that says sine, you get the idea. This is going to be a sine wave. Now, all of this stuff, there's a sine wave, and there's some multipliers in here. Just accept the fact that what's going into this waveform table is a sine wave that goes from 0 up to a value of about 255, and then back down again to a value of about 255, and then back to 0. So I'm getting a single phase of the sine wave, and it looks like this. Over here, I created a sawtooth using the famous remainder function. So you'll listen to trust me that this is a normalized sawtooth wave stored as 120 digits, and this is a triangle wave with this nice little equation here, stored as in 120 digits, one phase of a triangle wave. Then what I'm doing is I am simply writing those waveforms out to two different pins. You'll have to trust me that this is pin number 3 and this is pin number 11, and I'll show you why that has to be in a minute. But for right now, what we're going to do is I'm going to play wave 1 out of pin 3, and wave 1 is the sawtooth, and wave 2 is the triangle is going to come out of pin 11. All right. So we go back down here. Go back down here. Now, what I've got is my little, I've got a, what is this? This is a 47K resistor. And this is a capacitor, and I'm reading off, and the capacitor is going to ground, and I'm reading off the junction between the 47K. So I'm charging up this capacitor through this 47K resistor. And I'm reading off of pin 11. So as you remember, pin 11 is the triangle wave. Let me turn this bad boy back on. And now we're going to go look and see how well we're integrating when we go look over here at the oscilloscope. And boy, that doesn't look like a triangle, does it? Looks kind of like some bizarre sine wave, and it's really noisy. I mean, look at all this. The inside's fine, you know, it's kind of average right, but you got all this noise. Matter of fact, if we spread that out, look at all that. That's ugly. That's kind of ugliness there. All right, we're not getting very much of a triangle wave, but it is sort of integrating, and it's giving us a sine wave. This is not what we want. All right, let's try something else. You know what I'm going to try to do is I'm going to change the value of that resistor. Okay, so here I have a, what is this? This is a 1K. Okay, this was 47K. I'm going to pop the 47K out. I'm going to put the 1K resistor in. Let's see how well we do with that. All right, now when I come back here and look at how the integration is going, and oh boy, we got a triangle. Okay, it's still kind of noisy and ugly, but I got a triangle, and actually it's got a little bit of overshoot here. Because it's charging a capacitor. When the capacitor discharges really fast, it can undershoot below 0. So this is 0 volts, and you see we got some junk below 0 volts there. But generally, it's kind of triangle-y, and if I wanted to use that for an LFO, let's see, what frequency is it? It's 114 hertz. So I could slow that down and speed it up by changing the clock rates and the prescale on the Arduino. So that could be, you know, that could be an LFO, but man, look how noisy it is. I guess I could put some filtration on it or something. I don't know. That just looks kind of rancid. And the other thing is that what value of resistors do I use, you know? I tried the 47K and it just gave me garbage. And then, you know, that didn't look like a triangle at all. And then I'm trying the 1K works. But you know what? You're going to have to trust me because I'm not going to go through all this on camera. But the 1K doesn't work all the time. It doesn't work for other waveforms. It doesn't work for squares. You wind up overshooting and it's just a mess. So the truth of the matter is, even though you can make a poor man's DAC with just a resistor and a capacitor, for the system that we want to do here, where it's reliable and we don't have to be switching in different kinds of resistors and everything, you know, I guess the other thing I could show you is that it's not particularly, it's very noisy. I decided that we would use this professional DAC here. So what we're going to do is now I'm going to show you, I'm taking the output here. So it's not the output that's going into this little capacitor here. Matter of fact, let me just take that capacitor out of the circuit. So now that's completely out of the circuit. And it's going into this DAC. And I will show you the output waveform that I get over here to the oscilloscope. And there's the waveform that we get out of the DAC, the professional DAC. So that's a 12-bit DAC and no noise. I mean, it has a little bit of noise, little tiny bit of overshoot. We can see a little bit of quantization. Every DAC is going to give you some kind of stair stepping because that's the way it does things. But man, that looks like a nice clean wave. Now, on the other channel, I believe I had the sawtooth. I'll show you the other channel right there, and that's a beauty of a sawtooth. Little noisy, a little bit of quantization, but certainly not the kind of problems we were having with the with just the plain capacitor. All right. Now, just for grins, let's take a look at what the input to this is. All right. So this is the sawtooth, and I'm going to show you what the pulse width modulation for the sawtooth looks like. That the input that's creating this wave. Okay. So here's the pulse width modulation that's creating that sawtooth. So if I can freeze it. So what you're seeing here is I just froze it. So as we've got the wave and it expands a little bit, expands a little bit, expands a little bit, and as you add up the size of all of those squares over time, they get bigger and bigger and bigger as this expands, and then it snaps back down to a smaller value. So I turn that back on again, it snaps all the way back down to zero. It's hard to visualize. Going kind of fast there. I could let me see if I can slow it down. Hang on. Well, I have to slow it down by modifying the program, and I don't want to do that right now. But the bottom line is what's happening is we're starting out with nothing, just a single little dit here, and then the wave expands, 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 and then shuts down. And the result is that. The result is we're integrating, 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 integrating. So that's how that sawtooth was. Let's see how the triangle looks. Let's take a look at the triangle just because we're here and we can do it. So that's a little noisy because I had a nice little resistor in line in this one. So a triangle doesn't look too much different. You'll have to trust me that it's oscillating back and forth that way. Instead of just going up and shutting down, it's going up and down and up and down and up and down. And then when we head back over to the output of this guy, I hope I picked the right channel. Did I? Yeah, I did. There you go. There's the output. So that's these are the waveforms we're going to use to generate LFO and EG for the synth. Very nice waveforms. Those are it's a 12-bit digital analog converter. Now, I don't need 12 bits. Let's get into some of the engineering of this because this is what took me 2 days to figure out. First thing that took me 2 days was mounting the thing. It comes in an MSOP 16 package, which is this little bad boy over here. Let's see if we can zoom into that. All right, so I've got one of these. I actually sent away and had one of these bare bones boards made, but I didn't take into account exactly how far apart they should be to fit on the breadboard. So that was a mess. So it doesn't quite fit right. It's kind of off kilter and everything. I've sent away to have a couple more of them made. The part itself is not cheap. These 12-bit versions are $10 a piece. Now there's an 8-bit version that's only $5, and I'm going to switch to the 8-bit version. Reason I'm going to switch to the 8-bit version is because the actual waveform can only be quantized with 8 bits. So the PWM signal that's being integrated is only 8 bits anyway. I can only get 8 different sizes of little squares that have to be integrated, and that means I don't need a 12-bit DAC. I just need 8 bits. So I'm going to switch to 8 bits. So what's happening here is the PWM is coming off of the Arduino. It's coming off of pin 11 and pin 13. This DAC is actually capable of integrating four signals simultaneously. I've got 2 going through there now, but you can do 4. It's got 4 channels. So I only need 2 of these to generate an LFO that would work with 4 separate VCAs for all of the the synthesizer. The other thing is I only need 2 of them to generate the EGs. So what am I saying here with respect to the software, and why is it only 8 bits? Let's take a look at the Arduino code. All right, now one of the first things you're going to notice here is, holy crap, what is he saying? What are all the? I mean, this doesn't look like Arduino, does it? Well, I hate to say it, but it is. So one of the problems I had right away was I tried to use the Arduino analog write command. Analog write in Arduino just creates a pulse width modulated output. The problem is it does it the way it wants, and they figured out some kind of, one size fits all scenario that kind of works for just about everything, but it doesn't work for this application. If you're trying to decode the PWM with this, and here it is, there's the data sheet for it, the Linear Technology LTC 2645. If you're trying to decode the PWM for that, you're in trouble if you use analog write. You're in trouble for a lot of reasons. One is you can't get the frequencies you want. You can't, I mean, in general, you get a lot of aliasing, and aliasing is what happens if you try to represent a signal using a digital technique and a frequency that is not twice of the frequency you're trying to represent in your analog size. So what does that mean? So that means if I'm trying to make an LFO that runs at 20 hertz, I need to have a way to create a 40 hertz DAC signal to output my LFO. Well, that doesn't sound so bad. 40 hertz. Wow, that's way, way low. We run at gigahertz and megahertz, kilohertz. Well, it turns out that is kind of bad. And at the maximum frequency I've been able to get out using analog write is about 8 hertz total. Now, why is that? One is that the way this guy works is we're using the timers inside the Arduino. Arduino 328, which is in this Arduino right here. The Arduino 328 is in this Arduino Pro, the Atmel 328 rather. It's got 4 timers in there, 3 timers, timer 0, 1, and 2. And those timers, output of those timers are set to certain pins. We're going to use timer 2, and it's attached to pin 3 and pin 11, and that's in hardware. You cannot change that. What all of this does right here is it sets up something that says, okay, for timer 2, I have a bunch of variables I want to set. One is this sets timer 2 to something called fast PWM mode. All right, we could have a whole nother hour on how to program AVR. And I am not the guy to teach you. All I know is I just read enough of the data sheet to figure this out, okay? And you have to go to the data sheet and you got to figure it out. And you can put this stuff in your Arduino code. This is AVR code. This goes straight to, AVR dude or DUDE, whatever they call it. The Arduino compilers just pass this right on to that. And the Atmel compiler knows how to handle that. So you got to go straight to the hardware. You got to go to the Atmel hardware. You got to modify the way the timer works. You got to program the timer, and then it works fine. You saw the quality of the waveform we're getting out there. And in fact, I can get waveforms all the way up to about 600 hertz, which for an LFO would be just fine. For an oscillator for music, that would be no good whatsoever. That's why we're going to use the Analog Devices 9833 for that. But for an LFO or for an EG, that would be fine. So what we got to do is we got to create. We set these bits. This sets bits, and you can look up how that works. And if there really is anybody watching this in any interest, I will go through the data sheet for you and go into the whole thing. But I don't think we got that many viewers. In any case, this sets up fast PWM, and this sets the prescaler to 0. We're not prescaling. What does that mean? The clock on the Arduino is running at 16 megahertz. 16 million oscillations per second. That's 16 million counts per second. The way the PWM works is it's got a little counter. And the counter starts at 0 and it goes 1, 2, 3, 4, 5, 6, 7. And when it gets to its max, it resets itself to 0. When it gets to the max, when it restarts, it may set the output to high in the PWM. And once it gets to the top, it may set it to low and come back down and then set it to high and get it to low. And so there's a way that you can create that waveform with a counter. If you set the typically nobody wants to count from 0 to 255 at 16 megahertz. That's a pretty fast wave. Or let me say, people do they want to count at a slower speed than that. And so what the Arduino people do in their analog write command is they set the prescaler automatically to divide by 64. So you're going to get 16 megahertz divided by 64. So it's not really running at 16 megahertz. It's running at some number of kilohertz. Then you're trying to write out the values in these various wave tables, 120 of them. So you're actually going to divide by 120 again. And then, so you're basically dividing by 64. You're dividing again by 120 because I have 120 samples here. If I had a smaller number of samples, that'd be great. It'd go faster, but I'd have less resolution. So at the end of the day, when you start doing all this programming, the frequency goes way, 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 way down. So I set the prescale to 0, meaning I want my counters to run at the full 16 megahertz. I want to be in fast PWM mode, so I set that. And what I did down here is there's these two registers, these two variables. And the counter for the PWM generator counts up to or down to whatever the values are in these tables. So when I set the table to 0, the counter starts off and goes, oh, it's 0, I'm done, right? And it clicks the waveform off, that's fine. Then it turns the waveform on again, and the next value it says, oh, I got to count now to 100. And it counts up to it, turns the waveform on, counts to 100, gets to 100, counts off. So as I pan through, as I sketch through these tables, I'm setting the value in the counter over and over and over and over and over again. And that gives me the PWM amount that I need to create the waveform I need. My idea is for EG, for LFO, that makes sense. I've got these predefined waveforms that I put in here, and I just cycle through the table. I've also added a delay in here of 100 microseconds. That also helps set the frequency. If I turn this all the way down to 1 microsecond or turn it off completely, I can get to, as I said, about 600 hertz. I'm running at about 100 now, I think. And the way you figure out the frequency is a complicated mishmash of the prescale and the number of samples you have and the number of microseconds you wait, et cetera, et cetera. It's all timing. I'm not worrying about that right now. But the thing I'm going to tell you is that the way we're going to do the EG is we're going to set up an ADSR waveform in one of these variables, in one of these tables. So as we set an EG, I got to set attack, sustain, decay, and then release. And I'm going to store those numbers. I'm going to create that waveform, and I'm going to store them as numbers in one of these tables. And so instead of going through a sine wave, a sawtooth, or a triangle, I'm going to go through the ADSR, and I'm going to set this pretty low so that it, the frequency is only going to be, maybe 1 hertz or so. Actually, it's going to be user settable, but it'll be fast enough so that you can hear it musically when your fingers tap the keyboard. So that's the theory, okay? And there's a lot in there. I realize a lot of talking, not a whole lot of showing, but this took 2 days to figure out. So key points, again, the key points are that we're going to use, in order to get a good PWM waveform out that we can demodulate, we are going to use timer 2. That's connected to pin 3 and pin 11 on the Arduino. We're going to use pin 3 and pin 11. I'm going to get 2 waveforms out of the Arduino. I can get more, but I got to use different timers, right? So I think I'm only going to get 2 per Arduino. I'm going to get 2 waveforms out. I'm going to use this linear LTC 2645 to demodulate those and create the waveform over here that I see on my oscilloscope, which I will use. In this case, this is a pretty nice LFO-y looking wave. And then I'll also have it create an EG. Now, I could use the Teensy, I could use a Mega, I could use some device that has a really good digital analog output. I think I'm just going to try to do this brute force with an Arduino now, because look, I'm creating PWM and then I'm uncreating it. I mean, we don't need the PWM for anything. Be good just to not have it in the first place. But I'm hoping if I can keep this thing down to the simplest components, we might have something unique here that we could build out of just plain Arduinos, which would kind of be nice. I'm doing it kind of the expensive way first, but as time goes on, we can redesign and cheapen it. Let's see. What else can I tell you here? We got the VC. So I told you about the boards. We got the VCA boards in. We're going to be building with those soon. Oh, last thing. I've got to condition the signal. The signal's coming out of here. Actually, let's go back here and take a look. What we got here. Hopefully it focuses sometime in the near future here. Yeah. So we're at 2 volts per division. So I'm getting, this is running at about 2.5 volts. The output of the DAC is 2.5 volts. In order to run these 15-volt circuits, I've got to create plus minus 15 volts out of that 2.5 volts, okay? So this bad boy is going to run at 15 volts. So in order to control the voltage with this VCA, the control signal has got to be between negative 15 and positive 15. So we got to condition this signal a bit with some op amps. Same as with the VCOs. I've got to condition the signal. Right now this is going between 0 and 5. I've got to generate a plus minus voltage out of here so that it works appropriately with the rest of the circuitry. The analog circuitry is going to be run at plus minus 15. The rest of it is going to be at 0 and 5. Okay, and just a quick demo. So we've got the pulse width modulation from the Arduino going through DAC, creating a wave, which I'm amplifying with a little TLO82, and it's a little sawtooth. It's only heading down to minus 10. It's going up to plus 15. I have to work on the symmetry of that. Here's the VCA, one of them that I hastily put together. Based on a 13700, and I'm just using this little audio generator because if I had to put this guy on the same desk with all of this, there'd be no room. Alright, so what we can hear here is that's the VCA modulating the output with the triangle or the sawtooth wave on the from the EG. Let's I'll switch to let's see if I got it here. Alright, now we're going to see, now we've got a triangle, and you can hear the difference right away. I'm just using this little 10-mud generator, 800 hertz signal. So the VCA is here, plus minus 15 volts. I really haven't explained that in this video yet. And I'm just using a simple op amp and a whole bunch of little potentiometers so I could set it right. Obviously I don't have the symmetry set right because we're only heading down to minus 10 and we're going up to plus 15, so I'll have to mess with that. But generally speaking, it looks like the VCA and the EG idea are working. Now, to do an EG with a real ADSR, what I'll have to do is modify the Arduino code so that instead of just putting a sawtooth or a triangle into that array, I'll put an actual waveform. The other thing I want you to notice is, let's take a look at this waveform closely and let's see if it'll focus on it. And what you might notice is this stair stepping. So I'm using a 12-bit VCA, but the truth of the matter is the Arduino is only capable of producing pulse width modulation in 255 increments. It can only do 8-bit. So I don't need to use a 12-bit DAC here. I can use the 8-bit DAC. The other thing you'll notice, I have it, the triangle's kind of cut off at the top. I got to tweak these potentiometers to get that to be a much more symmetrical and pointy wave. But for the sake of a demo, you can hear that it basically works. Working soon, and you guys will all have a look and hear and see and hear it. I'm Joe. I really, really, really appreciate you stopping by, and please, if you think that any of the work I've done is worthwhile, please give me a thumbs up, or just let me know you're there, a comment or something. It'd be great. It does take time and effort to do these videos. Otherwise, I'd just be building this myself in my room and wouldn't have anybody to talk to about it. So I appreciate it. Thanks so much. Bye-bye.